welcome to my talk. It's nice to see you here. And we are going to do really crazy stuff. So maybe Lambda core, HardCore. Yeah. One thing about me, very shortly, I live under this mountain, over this lake. It's a really great place. Yeah, I'm a developer, wizard, and an architect. That written. I somehow devoted my life to JVM, at least the last 17 years. So a short time, but still something. I'm working with those technologies, hate all of them. I work for this company, it's CSS Insurance, basically. That's the name. And yeah, we don't really insure style sheets yet. We do insure people, health, etc. Funny thing about the company, it's started in 1899, so you know we have a legacy code. I mean Java EE, really. But okay, it's not gonna be about Java EE. So as first warning, you have really last chance. This talk is absolutely useless. Sorry. Sorry to say, if you are thinking about some funny stuff with Java, Java 8, details, how Lambdas work, no, it's not going to be about that. You won't learn how to do things, faster. It's absolutely not about that. So what's going to be about? It's about numbers. What is a number? So it's going to be, what is a Lambda Calculus? Lambda Calculus, who heard about Lambda Calculus before? Oh, great, so it's really a repetition for you. For others, it'll be, and how to do it in Java. That's probably the most important part of this, and then we'll have some fun. Okay. Yeah. So, I'm not a scientist. Sorry for that. You may have this impression, but not at all. However, I've studied mathematics. There is a reason. So people sometimes ask me why I've studied mathematics, not computer science. I didn't really study computer science, and there is a reason. Because at the moment I was studying, I had this computer, Commodore 64, and I was able to do that, especially this trick. So, really, for me it was like, come on, there's nothing I can really learn at studies more, because that's probably the masterpiece, what can a human do? And luckily for me, I had a colleague with the same problem, because at the same time he had his 286 PC, and he was able to do that. So he had the same problem. Nothing more one can learn at studies, yeah? Absolutely. So he had the idea, let's study mathematics. That should be something challenging, at least. So we went to the first speech, so the first lecture during the studies, and that was amazing. The teacher, the professor, was showing us the theorem and the proof that 1 is not equal to 0. It took a couple of minutes. So after this, I would say he was very successful because we believed in this proof. But it was the first time in my life that I started to doubt. But okay, nevertheless. So we'll think, what the hell is a number? We'll talk. So who has idea what is the number? Because, it's very easy. Let me do, those two letters. Like this. This is one letter. This is a second. So I have two letters. Those represent concept of 2. You agree? But what if I don't have letters? What should I take? Maybe people. They're going to help me. Let 2 people stand from the first row. You both. Just stand. So I have 2 human beings to help me in mathematics. So you understand probably, thanks you. You can sit down. It is okay. I can say maybe for calculation, let's use people. But if I'm going to count something like, 100 plus 100, I'm gonna really need a huge room for that. Yeah, you agree? I would need a lot of people. So, and then comes the problem, because this is very interesting. This is 2 Polish zloty. So, 2 Polish zloty. And for me, it's a problem, because it's 1 coin. How can it be 2? Okay, so maybe behind the number is something more, and we're gonna discover this. So let's pretend something strange happened. So let's talk about this too. You know what this represents? It is a Big Bang. The way, the moment the universe was created, okay? And then everything happened like metal to create this 2 zloty, or to things to create these letters and humans and everything. But what if the universe wasn't created, hasn't started? There was no Big Bang, and there's alternative theory. It was created by flying spaghetti monster. So let's pretend there was no flying spaghetti monster. For a moment, let's think about this possibility. So universe wasn't created. Can we have numbers without help of humans, letters, apples, whatever? The question is, how? So in the universe, maybe, so that's a classical approach, maybe we can introduce a concept of set. Who knows what the set is? I don't know. I studied mathematics, sorry for that. And mathematicians say, by the way, by definition in classical mathematics, don't define set. It's too complicated. Let's pretend they exist. So we have universe, and we say, let's think about sets in universe that wasn't created. It's empty. Nothing is there. Not a single item. Can we create some kind of set there? Can we discuss about sets with nothing exists? Who has idea? Is there any set that you can have in an empty universe? Come on, help me. Empty set, that's great. That's mathematical concept. We have an empty set. So it's crazy. Universe wasn't created, and we have empty set. That's already one thing. Nothing exists, and we have one thing, empty set. That's great. That's good start point. And mathematicians really, over 100 years ago, followed this rule. So we have one thing, and it's easy, because then we can create, we can one thing, empty set, we can put it into another set. So we have set of empty set. How cool. So we have two things. No flying spaghetti monster, help, and we already have two things. How great. And it goes further. There is even procedure. I won't explain that. But generally, that's a set containing an empty set and set of empty set. It's another set. There are different. By the way, it's hard to prove they are different, but they are. But if you look at this, that's a 0. That was the problem, how to differentiate those things. That's a 0, that's 1, that's 2, and that's our operation of successor. I won't discuss that, but that's a classical definition how mathematicians define numbers. Because they really want to discuss real life case. So real life case, let's pretend universe doesn't exist. So that's a 3, whatever. So it was okay. Why did they do that? Because, discussing numbers like we do it classically would be quite naive, because they had idea. If we really study well the fundamental bricks of mathematics, what's there? If we define all the rules pretty well, we can reach a funny point. Because maybe if our rules are good, the Holy Grail will happen. What's the Holy Grail of mathematics? If our rules are consistent and are full, we may find an algorithm that would tell us if some statement like theorem, like Pythagoras theorem, is simply true or false. So like a machine that will be giving any random theorem, like, I don't know, 2 plus 2 is 4, yeah? And this machine will be saying, yeah, true. And we'll do some other, like, I don't know, some more complicated theorem. At the moment, I don't really, Fermat theorem, whatever, and the machine will just analyze it using all these basic rules, maybe with a sets, and will tell us, is it true or false? That would be great. Let's build that machine. So that was the Holy Grail. And, they started to build this theory. It was looking really good at the beginning, but then came a problem. That's one of the fundamental problems of this set theory. Let's consider the set of all sets that are not members of sets. It sounds crazy, but let's rephrase it. Yeah, the question is R member of R? Don't really try to dig into that. It's already too late, and you will going to need a drink after. Anyhow, you're gonna need to drink after this talk. Anyhow, so let's rephrase that. That's the really popular, you will find in the Wikipedia, rephrasal of the same statement. In the city X, maybe it's Bucharest, I don't know. There is a barber who shaves all men who don't shave themselves, and only men who don't shave themselves. Okay. And the question is, should the barber shave himself? If he shaves himself, he cannot. So it's crazy. And that is, in fact, called Russell paradox. It really is the same problem. And this is in this really nice theory of sets, how we defined numbers, came such paradoxes. And there was a problem what to do with them. So the answer to that, oh, sorry, that's a web page, so I have scaled it. The answer to that was, let's build some other actions that would forbid such event statements. And it's exactly happened in mathematics, what happens to your project every day. You start with a really good architecture. It's clean, it's very small, it's very concise, it's everything, and then comes a business with paradox requirements, and and the whole your architecture fall apart. You have to, really, if you look at the seed theory, there is like 5 really good actions. So these building blocks, what we do? And then 7 others that are just, what? That's really those hacks you had to do in order to make all the things work for the business. Okay. So, you know what we do in our systems when our architecture falls apart? We try again with a different sometimes. Mostly not, but sometimes we try with something different, like, functional programming, reactive programming. We fail anyhow, but we try. So there was a guy in 30s from the last century, Alonzo Church, who know this guy. I mean, he must be very old, but nevertheless, he really did fundamental changes. So he said, oh, maybe the set is the wrong brick, wrong building brick. Let's start with something completely different, a function as a fundamental thing. So let's build everything on a function. Oh, how cool. So who knows what the function is? Nobody knows. What? Very quick, that was very quick. You know, what's the function? Yeah, so good answer from the school. So it's crazy, because how can we have a function when we say sets are bad? It's crazy, but okay. We will show this. So let's start. Let's start. There is no universe created. We have empty thing, void, nothing. Can we have a function there? What? Okay, but we would have to define it. Now, so is there any function that you could describe to someone else, not really using any objects? So you are forbidden to use natural numbers, so you can say function plus or minus or whatever. And there is indeed some kind of function that really is similar to an empty set. It's so as much useful. Yeah, identity function. So what does identity function? Does nothing. So whatever this exactly is. So if I take this thing, then identity function will return the same thing. If it takes bottle, it returns bottle with water. Yeah. So does nothing. But we can discuss this function. Okay, in the example I showed the bottle or whatever, but for its existence, it doesn't need anything. We can discuss about it. Like, cool. So we have again empty world, empty universe. Nothing exists, but there is one function. How cool! So we started with something. It's great. So that's exactly how mathematicians represent something that's identity encrypted. So in Lambda Calculus. So it's very easy. It's only just a code. Lambda means a function, let's say, that takes argument x, and after dot we say what happens. We return x. So it's identity function, just to make things more complicated. Yeah. Okay, let's talk about these lambdas. We're gonna need them. So it's just standard form is lambda from some kind of variable, like in this case x, and then expression. After the dot we have expression. So what we are going to do? That's just a formalism, how we define lambdas, yeah? And so maybe we can say that plus function is, let's take, okay, so it's like double. Let's take x and return x plus x, or let's take x and return sinus of x. The problem is, we are in empty universe, we don't have any plus or any sinus. Come on, we have to create them out of something. They don't exist. So those lambdas are okay for describing what the lambda is, what the function, but we cannot be, that's not gonna be that easy. We have to create mathematics with some fundamental blocks telling what the plus is. And we're gonna do that. So maybe there is one thing that exists also that we can use. So that's the lambda definition, one thing, in formalism. And the second thing we need is here between quotations. It's so important operator in the Lambda calculus that mathematicians are afraid to write it. Because of that, they have chosen white space. We don't draw it. It's too, too big to draw it. So that's a white space. That's the most important operator in something called Lambda calculus. And what do you think does it mean? It's a function application. So, every function is eager to be applied to something. So exactly in Lambda calculus, we use nothing, so white space, to show that something is applied. But maybe there is a little bit complicated case here. So not complicated. X is some kind of lambda. Y is another lambda. And here is a space. Means y applied to x, or vice versa. I have always problem how to write it. This is more complicated case. Let's have lambda from x that is f applied to x. And then let's apply it to y. And then, so if we do this application, for x, we say y, we will get f applied to y. That's a result of this operation, of the applications. Hope it's easy. It's like a normal function. It's only written in a stupid way. OK. Well, you will see that even better. So let's go to Java. This is a language that you probably, who understands Java? Great. That would be easy for you. OK. So let's define lambda in Java terms. Yeah, how cool can be that? So maybe let me start. It's like, it's interface lambda, and it would have one function. I already started. One function in interface. What can that be? Function that returns lambda. It would be called apply, and what it takes as an argument? Lambda. How cool. You see how great is this interface. We only have one thing, lambda, that eats lambda, returns lambda. That's everything we need to create mathematics. It's great. So let's play with that. So let me play with that. I have public static void main. So blah, lambda, identity. That's identity. You understand it better. It is lambda. And maybe let's do a stupid thing. Let's print it. Why not? What will happen if I print it like that? Stupid, yeah? Let's compile. It's very, very big project, so I'm using Maven because of that. It's very slow. But you see, yeah, it gets some result. It's stupid, but we can already do something. Oops, sorry. Just a moment. I screw something, but I will do it better. So once again, I'm here, and I do one more line to show you that everything works. So I will write this: system out println identity applied to identity. How cool! What will happen right now? It works. Identity returned the same. So okay. By the way, of course, in this universe, system out println an empty universe doesn't work. But doesn't exist, but we use it only for debugging purpose. Yeah, I could write identity apply identity, but not displaying it anywhere would be a problem. So that's a kind of shortcut. So there will be such small shortcut, but okay, let's discuss lambdas out of nothing. Let's go back to mathematical, so you'll understand how simple lambdas are. So let's consider this lambda, because creating identity is easy. How to do next step? And this is exactly a next step. It's really, really brilliant idea. Let's take lambda from x, and by the way, that's the result, that whatever it takes returns identity. That's identity, So it's take an argument and just neglect it. You are not interested in x, I will return identity. So it's the second lambda that we can create in an empty universe. By the way, it's function of two arguments. Ignore the first, return the second. If you look at this, yeah? So maybe to show it, how it works, we have this lambda, and we have borrowed from the second universe trumpet and tomato. And by the way, I'm not mathematician, so I'm not afraid to use operator. Here are underscore is this white space. So let's take this lambda, and apply it to the trumpet, and then apply it to the tomato. So in the first case, trumpet will be placed in x in this expression. But as there is no x, it will simply return this expression, and then I will live with a second argument. And this time I have identity lambda, so in place of y will be tomato put, and I get, at the end I have tomato. How easy? It's great. So I have already 2 lambdas in universe that wasn't created. How cool. So can I create some more lambdas? Anybody have idea? Of course, but there is another step, almost identical. This. It's really great. Let's take x, and then return a lambda that takes some y, and still returns x. So in this time, we were just postponing, we were ignoring x. In this time, we're ignoring the y. By the way, those are only names. It doesn't matter what names are out there. It only must be consistent with this expression. So in this case, if we take this lambda, apply it to the trumpet and to the tomato, we'll get this. Lambda from x and then trumpet. In place of x, it means it will be put here, trumpet. So after the first application, I will get this. Lambda from y is trumpet. And then I will get tomato. But tomato in place of y, come on, there is no y. So at the end, it returns trumpet. So I had empty universe and 3 lambdas. How cool. There are more. Maybe, OK, it's not really correctly written. Let's pretend here is the white space. I somehow forgot it. So it means let's take x, let's then return a lambda that takes y and returns x applied to y. It would be great, but the problem, if I apply at the end trumpet to tomato, I would destroy trumpet on tomato, and I borrowed it from other universe. I want to return it in the same state as before, so I cannot show you that. But nevertheless, there are more possibilities. We are really powerful. So let's play with Java. That's Java. You see that? Hopefully it's readable. So maybe system out, and right now, a small trick. So what I will be doing, I will be only using lambda definitions. No integers, no booleans, whatever. Only definition of lambda. And inside of this definition, I am able to reuse other lambdas and do function applications. But there is one thing from the external world. I would like to show you the results. And to show you the results, I have special library. That's something borrowed from other universe, from this universe, right? Like the one that was created. It's called Smart Display. It's a very stupid library that takes a lambda and displays it in this mathematical way. Just this, nothing more. We don't need that, but for debugging purposes, to make it easier, I am using that. It doesn't change the way it works. So I will just display it to show you how it works. Like, let's see that the library works. By the way, there is mathematical proof that says, I will even show you, that this library cannot work. No worry, I've written it. I'm a wizard, so I don't have to follow mathematical rules. But basically, it doesn't work. But still, I am using that. I need it. So let's define this funny lambda. This is funny lambda. From x, yeah, let's display it. Sorry, not here. Let's display it here. Nothing really funny here. Like this. May even be faster. Come on. Yeah. So we have, this is how I convert lambda written in Java to the mathematical encrypted version. Cool. Let's play with that even more. Lambda at true. There is a reason why I call this lambda at true. No, I will show you. And as you see, this lambda looks same as funny. It's the same. By the way, lambdas, the names of the lambdas here, do not really matter. If it's called funny or a true, it's the same. So in any place I will use this, I could use this, or even can create. It's only a matter what's written here. But for some reason, I would like to show you this with a name true. And let's display it. There will be no real, I would say, surprise here. If I display it, it should just display twice the same thing, like this. Cool. Who would expect? So let's do something else. Let's do false. So false is this lambda. Nothing really also surprising. This, we have true and a false. And let's display them. OK? what will happen? Yeah, like this. And right now comes the real magic. Let's define another lambda. And this lambda is something I will call end. And by the way, I could use here x and y. Of course, it's possible to use x and y, but in Wikipedia, if you go, by convention, they use p and q. That's a mathematical convention. I didn't want to break this convention, so to make it more readable and so that you are able to compare it to some standards, so I used symbols p and q, but it doesn't matter. It could be x and y, or whatever, a1, a2, variable 1, variable 2. And then let's display it. And by the way, if I display it this way, maybe I will show you how the library works. It's very simple. If I display it this way, it would do this, that at the end I will have this with x and y, but I have built some kind of the thing to make it compatible. If I say with WebP, that means do it with P convention, and then it's all nothing magic here. Just analyze, just lambda displayed. And now, you know, it's not coincidence why they are called AND, true or false, because I can do something like this. Blah, blah. Result 1 is AND, apply false, apply true. Okay? And then let's display it like this. And now should magic happen. We took this AND lambda, true and false. And what was returned from a false and a true? What is this? That's exactly the same what we call false. So AND of true and a false return false. Oh, no surprise. That's mathematics. That's Boolean calculus. So great. So maybe let's see if it works. If I put here a true, then it should display. Great. Magnificent. So we have AND operation. You know, it's really great. We have empty universe, lambdas out nothing, and already we have AND operation. And if you studied something, you probably know that's almost everything that we need. So we have to go a little bit farther. So let's define this. Lambda OR, that's something like this. PQ, and let's display it. And even, I will not make it too long. Let's just apply a false and a true, and display it. That's result 2. Let's see if it works well. Okay, okay, so like this. So it's like it's defined operation OR with just lambda. You see, no plus, no Boolean from Java, nothing borrowed, only lambdas, definitions, and applications. Yeah, how cool. And then here I'm using this OR, applying a false and a true to that, and what I get? Something that looks like a true. It's OR operation that actually works. How cool, so let's see, let's prove that. If I use a false here, oh come on, a false, it should display me false. Yeah, it is false. Something that takes X and returns A identity. And by the way, I could even write here, B takes, I don't know, C and returns what? And returns B. What is this function? Who knows what's this? 2, that's true. So it's equivalent, it's the same as true. So as you see, the result is true. How cool. So we have something that works. We can go farther with that. If I do like, I don't know, not operator, it looks like this. I will show, moment, let me show you that. Not false, and let's see if not false is something that looks like true. Let me show you that. Yeah, not false. Yeah, it's really looking like true. How cool. So it's really, out of nothing, create Boolean calculus with lambdas. How cool. Let's go further. It doesn't end here. It's amazing. So, you know, Boolean calculus is simple. True, false, kind of few operators. That's really not numbers yet. Though almost numbers, but not yet. So let's go. Let's make it more funny. Let's define, oh, moment, I did something wrong here. Let's define that 0 is something like this. You know what is 0 in fact? You remember this lambda? We gave it another name. What is that? What? False. So you know why in C language, who knows C language? They already knew that false is 0. How cool. We are consistent with C. That must be true. That must be good. Cool. So 0 is something like this. But by convention, once again, see this web F means I won't display it with Y and X. I will display it starting from the F symbol because that's a convention in Wikipedia and standard mathematics used to display numbers, lambdas that represent numbers. So only that, nothing really magic here, only different letters used to display. So 0 is this kind of lambda, which by the way we know as false. That's not a problem. So let's see something else, something completely different. It's a 1. 1 is this lambda. F takes lambda that takes F, then takes X and returns F applied to X. How cool. Yeah? So let's display it. 1. Okay. So you see, that's 1. Now, where does it go? So lambda 2 is like this. You will see the pattern here. You'll see the very interesting pattern. By the way, that's only convention, and that's not only the only way to represent numbers. That's only one of few conventions. That's the most popular one. It's called church lambda encoding. There are different, but this is the most popular. So let's take a look at 2. What is a 2? In this convention, we call 2 this lambda. And by the way, there is a simple mapping how the numbers you know mapped to lambda. Just count the F's. If there is no F, it means 0. If F is once applied to X, it means 1. If it's twice combined, then it's 2, and this way. So it would be easy for us to convert between those. So maybe we can define operation of increment, successor. It's great. So successor looks like this. Oh, horrible, yeah? Well, it's magic, but let's see. Let's print it. And then let's see what will happen if I display this. Okay? Moment, let me do this. Like successor of 1. I'm curious. So successor of 1, if you see, it's the same as 2. So it really works this way. So we have incrementation, we have 0 numbers. So great. We have all natural numbers. They are great, but you know, for natural numbers to be useful, we need some operators like plus. So let's define a plus. That would be great if I could do that. Okay, so moment, just successor of 10 I'll print before, just to make it easy. By the way, I forgot about one thing. You know what's this? I was really angry writing all those F's, this lambda, so I created. You can take a look at this library, Smart Display. That's conversion from Java integer, and that's only for this, that at the end creates a lambda, really from lambdas, that represents this 10. So it's how to convert between two words. By the way, it's not needed. I could write it F 10 times and this lambda, but it would be boring. So let's see a lot of F's. Let's see them. Yeah, you see this. Yeah, it's this way. So right now, come to plus, because yeah, plus operator looks like this. Oh. Horrible, isn't it? But you know, if it looks stupid but works, it's not stupid. So let's check. Plus, I'm gonna display plus. Once again, another convention. I use different letters, and then I create lambda that is representing 6. Again, I'm using this conversion. I could write F with arrows 6 times. That would be boring. So let's write it this way. It's really the same. You can check. Code is open source on a GitHub, so you can check it. So I display A to really show you that it's this lambda. Then I will display B with this lambda. And then I will display plus A, B, yeah, web F, display plus, apply A. It looks stupid, yeah, but does it work? Oh, come on, please. Maven, be faster. Yeah. So we have 6 here. We have 7. You can count these F's. And then I'm very bad at counting, but you can do at your own. How many F's are there? 13. If it's 13, I hope it's 13. It means it works. We have a plus. So I may even, let's be somehow crazy with that. 60. So it's probably the biggest number wow. And it works. If you see, we can see that there are a little bit more F's here at the end than here. Probably 7 more, but I don't have time to count them. So we have plus operator. So wouldn't it be cool to define, so with plus, 0 incrementation, it really covers all the natural numbers. To make it even more funny, let's do something more. By the way, that's conversion to plus with, there is another operation, so here it was from integer, this to integer. It's basically, I call this function and count how many times f was applied, and this way I can even show you. Let's see if it works with this. So 67 times it was called. So it's like how to convert between two wells, but it's not nothing really that we need. It's only to, so let's define multiplication. It looks, looks this way. Yeah, moment, just let me print it for you better. Multiplication is like this. We'll display it. And then, okay, you know, I'm gonna use smaller numbers. By the way, I won't count all of them because it would be stupid. I'm converting into integer, so maybe, I never tried to really run it with 60 and 7 and then convert to integer. So the function will count how many times f appeared. To not print it on your screen. Whoa, how cool. Really worked. If you don't believe, I can make something really crazy. And I can display this. Smart display. Oh, it was in fact displayed here. So it's great. So we had this big number of f. So what else? I'm ending here. So we have plus and multiplication. We have booleans. Great. So, but you may say, come on, minus would be problem. No, come on, it's not. Let me show you that. Let's do something interesting. So it's a 9. So it means I will represent a 9 number and define what means -1, decrementation, predecessor. It's like this. And you know, that's probably one of the craziest operators I've seen in Lambda Calculus. Really doesn't end here. It's easy. Oh my God. Oh my God. Oh. Then I print it. Smart display predecessor. And then I print, what does it mean? 9, but one less than 9. Oops, sorry. There is an error here, as you see. Oops. Just a moment. Because I already knew what I'm going to print. Oh, my screen. You didn't do it well. You know what? I'm restarting this. Sorry. It's my magic engine. So once again, you don't see that. Again to this point. Great. Predecessor, great. Almost there. Yes. And as you see, if you count how many times I see f here, 1, 2, 3, 4, 5, 6, 7, oh, it's a 9. So 9, and right now, I forgot to put this line. Predecessor of 9, it's like this. Cool? You see, should be 1 less. It's 8. How cool? So we have. Then it would work this way, but so subtraction looks like this. I won't really play with that because we don't have that much time. I will do something more crazy. Lambda if. So because we have operators, mathematical, but what? How fun it would be to represent some concepts from algorithms, like if operation. You know if. What's done if? What? Yeah, branching, but this is a lambda. If is a lambda. Basically, if is a lambda of 3 parameters. So one is a condition. Then what are we going to do in case of true? And what we are going to do in case of false? And this condition, by the way, must be this true or false as we defined before. Okay? Then this looks like this. It's very simple. I don't really understand this, but it works. I will show you. Then we can even create such operator like is 0. And by the way, I'm using something strange here. I will explain you that. That's my Boolean. It's wizard Boolean, which this is a constant which in fact hides this false lambda as defined previously, just to not repeat every time the same term. So is0 looks like this, and it works. I don't have time to show you everything, but we'll go really far. So if I have is0, I can even use such operators like less or equal, which would moment, let me show you this way. Yeah, less than or equal. And then I will begin something really crazy. Because it's something really, the most interesting part of this. Lambda that is called autocall. That, by the way, it's the most root lambda that you can create. Really, it's like telling to someone, go on, do it to yourself. Like this. Take x and then x apply to x. How bad, how rude. But nevertheless, it's very important lambda, because out of that we can create another lambda. That's a y. It's this name y is in fact common, used for that. Looks very strange, but has anyone before seen this? You know what's this? What's this? Exactly, it's called fixed point combinator. And you know for what it's used? Oh, you are great, amazing. Exactly, we are going to use some kind of recursion. Why is recursion? Recursion is generally very hard in Lambda calculus. Why? Because, for instance, let's imagine that subtraction needs recursion. So I have to inside this subtraction called subtraction. If I try to do it like this way, maybe like this, then apply something, it won't compile in Java and won't compile in Lambda calculus because subtraction is not yet defined. So in this place, we cannot use that. That's the problem. So in normal Java, functions, they can call themselves, but in Lambda calculus, we cannot start calling the lambda that is not yet finished definition. That's the problem. And in order to fight with this problem, we have this nice fixed point combinator, okay? So let's do it. So like, I'm gonna use that. I'm gonna create very, very crazy definition. If lambda, that's an if. Oops, sorry. Once again. If lambda, apply is 0. So the condition, if I have some kind of 0 from n, then I will call, and here I'm going to use these cardinals. Cardinals is again lambda that represents 1. Okay, sorry. I'm really lost in this. It's too small screen for me, but I'm going to continue with that. Okay. Then, in otherwise, I will use some multiplication with predecessor. And then, yeah, like this. Let me see if it compiles, because it's like, at the moment, it's like, nothing really fancy. I don't really return any results, but this G. Has any one of you idea what the G is? What? It's almost factorial function, almost. It's a factory of factorial functions. So like factory in Java. It's something that you need in order to create factorial. And how you create factorial? You create it like this. Let's say lambda fact is like, factorial is y, and I'm going to use this magical combinator y, apply g. Exactly, it's this way. This is a almost factorial, and this y makes of this the factory real factorial. So something that works as a real factorial, and we're gonna see that. So let's see that. It's lambda. Let's define that a is 3, and then let's see what is this. Smart display. Let's display this a, and then display. What does it mean, factorial of 3? If you don't remember what a factorial is, we're gonna see this. It's with this symbol, the exclamation mark. So factorial of 3 is 1, 2, 3, 4, 5, 6. It seems to be sensible result. So I don't really know, but let's play with 6, for instance. What is a factorial of 6? This is gonna be tough. Whoa! So I counted all these f's, really, at home, and I know it's okay. But I can prove it to you this way, because I have this special function that really counts all the f's, and then I create the result. So we see how it is in the normal way of displaying 720. It's real factorial. It's really, so to conclude what we've shown, out of nothing, universe that wasn't created, we've created all the math with Boolean calculus, natural number, plus multiplication, and we even got to algorithms. We even were able to create recursion. That's cool. We have almost everything to recreate the world once again better. And that's exactly what happened. So that was the idea of Lambda Calculus. Let's create the world with a better axioms, better bricks, so that we will reach something. And by the way, that's a proof. It's in fact proven by Church that a Turing machine, so whatever you compute, and Lambda Calculus as Turing complete. So Lambda Calculus works on paper, Turing machine works on the long paper, but nevertheless there are equivalents. Whatever you can compute, you can do with Lambda Calculus. How great. It's really, Lambda Calculus is the smallest computer language that you can have. Really doesn't need anything, and it's already sufficient to do anything. Great. So that is great. So maybe then we can write like this. Let's pretend that we have some kind of theorem, like Fermat theorem, whatever. Maybe in mathematics, theorem, so something that we can prove, always looks the same, like this. If, and then condition, and then statement. So you know already if, we can represent if with lambdas. So this whole statement we can represent with Lambda Calculus. Yeah, so maybe it would look like this. Okay, and then, if it's like this, so what can we do? Create some lambda that will take this statement and will only say, is it equivalent to true or false? If it's true, that means the statement, the theorem is true. How cool. Let's build such machinery which will do that. And the problem is, it's very hard to do this because there are some nasty lambdas. So you see this autocall. You've already seen it, yeah? It's great. It works. We can display it. So autocall displayed is okay. Should be, oh, I did something wrong. Moment. What's wrong here? Nothing. I don't see an error. Once again. Or will you help me with error? No, it's not the problem. Stack Overflow. Oh, exactly what happens. That is, in fact, that happens here. The problem is there are such nasty lambdas, especially this omega, that is using this autocall. Whatever happens, it basically explodes. So that's a problem. It's that you can't analyze these lambdas. And this is a problem that's equivalent to problem that you probably know if you studied computer science. You know the problem with Turing machine. What? Halting problem. And exactly that's the problem. No computable function, so you can't really create such function that would tell you if the statement is true or false. It's the same, it's exactly equivalent problem. It's the same problem as you have with Turing machine. You can't build a machine that will analyze another machine and say if it stops or not. It's the same problem. It's basically the same problem behind. You can't do it. But by the way, people nowadays are doing that because they haven't studied maths. They don't know it's impossible. And in C#, they already went very far away. Test equality of lambda expressions. I haven't really studied it, what they did, but it seems to be working. I'm not even surprised. So, leads us to some really known problem. Who has heard about Gödel theorem? Yeah, so the problem is that sets were not okay. And it appeared that lambdas also are not okay to really reach the Holy Grail. And in fact, Church already knew that. Because even before Church created his theory, the Kurt Gödel presented this. That in fact, whatever you try, if your formalism, like Lambda Calculus set with the numbers, is good enough to have arithmetics, then for sure there are statements that you can create there that you can't prove them. Simply like that. Even in this, I don't have time to show you, but in fact the proof of this can be proven, by the way, and the proof of that is that Kurt Gödel presents a statement. Exactly, he presents a concrete statement that is true, but you can't prove that it's true. It's great. It's really used there. So, but I will show you where to go with that. So let's make a summary of all the things I have shown today, of this useless stuff. Lambda calculus. If you go to Wikipedia, you will get a nice explanation with all this mathematical formalism and encoded version. But you can do it with Java to really see how it works. You can even debug it. How cool. Then it will be way easier to understand if you are, for some reason, interested in that. And by the way, I have skipped a lot of real problems that happen. So for instance, eager, lazy evaluation. Even the bigger problem is, what would happen if I use plus function, and I will apply it to 6, lambda representing 6, and then maybe multiplication as a second operation, so not a number. In Lambda Calculus, this version I showed, it's untyped, so you can do anything. Then you don't know what happens. It's just crazy thing. But there is a version of Lambda Calculus, typed Lambda Calculus, that is in fact the basic formalism behind all the typed functional languages that solves this problem. I don't have time today, but basically there exists solution to that. And the proof that I really seen with that, you can really do everything with pure functional programming. I've shown you don't even need integers or floats, whatever. And by the way, it means there is no excuse for you. You for sure, anything you do in your work, you can do functionally. Of course, you don't have to be that strict and use pure lambda. Don't be stupid. But for sure, a lot of things you write in this pure imperative still, you can do pure functional. Not always it makes sense, but a lot, I would say it's more times that you don't use functional style or that you overuse this. Yeah, so it's look for places. And to read more, if you are for some reason you're gonna want to waste your life on this, Wikipedia is in fact a good source. There is a great blog which presents the C# version of this. It's called Dixon blog, and he goes really way farther with this topic. So you can spend basically months of your life reading and recreating and checking this. But he is really a great guy describing the things. Dixon's blog, and there is a great book which isn't really about Lambda Calculus. Lambda Calculus is there shown on 2 pages. But it's a great book if you want to think about the fundamentals of mathematics Turing machine. It's Roger Penrose's Emperor's New Mind. He really even presents the most important Turing machine with a number. And that's great, how he goes there. He presents really great what's a Card-Gödel theorem. He really recreates a whole way. If you want to visualize this lambda, you can use this Bedlam library from me. And by the way, it's proven to be not correct. Nevertheless, it sometimes works. This presentation, so that you can read link, you can find on this tiny URL, hard lambda, and that's basically all I wanted to tell you. Thank you. Do you have any question?